Okay, next part is on continuity. So now the chapter is a very important chapter in the analysis in general, and the name is continuity. And the idea, very naive idea, is that we are using the same definition as for the limit, but considering instead of L the value of the function at x bar. So the definition will change. I give you immediately the definition, then we will reason on the definition. So again, let E be a subset of R. This time x bar is an element of E. It is not an accumulation point of E. And F is defined on the domain E with real values. Okay? F is continuous at the point x bar if for every V neighborhood of f of x bar there exists a U neighborhood of x bar such that f of all the element, the image of all the element in the neighborhood of U is contained in V. Notice that there are many differences. So with respect to the definition of limit, we have first, x bar is an element of E, not a point of accumulation of E. First. Second, is the role of L is replaced by f of x bar. Third, the basis point x bar is not excluded from the definition. On the contrary, the role of x bar and of f of x bar is essential, is very important. Again, picture in order to better understand. Here we have this function, and let me consider x bar, for instance, here. This time x bar is in the domain, so there is f of x bar, which is here. And the definition says that for every horizontal stripe near x bar, f of x bar, okay, and this is V. There exists a vertical stripe that contains x bar, and we know now how to do it. So to say a neighborhood V. u of x bar, and this is the neighborhood u, or every other neighborhood contained in it, so such that the image of this neighborhood falls into the stripe, which means here that this part of the graph is red of the function, this part of the graph falls inside the stripe V. This is the idea. This is just a part of a definition. And with the next remark, I want to stress this point, which is extremely important and somewhat surprising. So we have a remark. Okay, we distinguish two cases. First, consider x bar to be also an accumulation point. So it is an accumulation point, and it is also a point in the domain because of the definition. Okay? Then does there exist the limit for x going to x bar of f of x? And if so, what is its value? Okay, this is the question. And now we remember that since f is continuous at x bar, then we know that for every v in u f of x bar, just definition of continuity, there exists a neighborhood u of x bar such that f of u intersection E is an element of V, but we know that if we consider f of u intersection E minus x bar, of course this is contained in f of u intersection E, which is contained in V. Then, by definition of limit, the only difference notice is here the exclusion of x bar. We have at the end that the limit for x going to x bar of f of x is equal to f of x bar. Okay? The second case, okay, this is quite expected, because here this is exactly the picture of the limit, but instead of L here we have f of x bar. And the second case is indeed f, on the contrary, on the other hand, x bar is an element of E minus dE, namely x bar as not an accumulation point of E, then And notice that here this passage is not trivial, okay? If it is not an accumulation point, it means that there exists a neighborhood of x bar such that in U, the only point in U that belongs to E is x bar. So U intersection E is equal to x bar. This is nothing but denying the definition of point of accumulation. Okay? So if I consider this U and I take the image of U intersection E, we have that here this image is just f of x bar, but f of x bar is an element of V, because V is a generic neighborhood of f of x bar. So pay attention to this point. The definition of continuity is fulfilled. Therefore, f is a continuous function at the point x bar. And this may be very surprising, quite hard to accept, but there's an important remark. Is the following. F is continuous I put it here in red at every isolated point of its domain. Here, isolated means not accumulation points. In particular, every sequence is continuous at all points of n, since all points of n are isolated. Okay, so sequences are continuous functions, even though when you draw the graph of a sequence, you do it by points. So you cannot keep your hand, you cannot keep your pencil on the sheet. I know in high school you have been taught that the continuous function is a function for which it is possible to draw the graph with the pencil always on the sheet of paper. This is not fully true. There is something missing in this characterization. This is true for continuous functions on intervals, but for continuous function in generic domains, this is not true. Okay? And so another example that we already know is the following. You consider the function f of x is equal to x squared x minus 1 So x squared minus 1, for instance. So we have that E is minus infinity minus 1 closed, union 1 closed plus infinity, union 0. And notice that 0 is an isolated point of the domain. Okay? And remember what was the graph of this function? Start from here to 1, and this symmetric here in minus 1. Okay? Okay, it is symmetric. My picture is not so symmetric, but just to give you the idea. And here we have that f is continuous at every point of E. Oh, sorry, here there is a 0, which is important. It's continuous at every point of E, included 0. And now what is the message, the main message I want to convey? We have that f is continuous at x bar in E if and only if first x bar is an accumulation point, and we have that the limit of x going to x bar f of x is equal to f of x bar. First. Second is if x bar is an isolated point of the domain. Okay, this is the main message. Continuity, the notion, the idea of continuity changes a lot according to the fact that the point in which we are evaluating continuity is an accumulation point of the domain or not. In the first case, this is an accumulation point of the domain, and we have that the limit of our x going to x bar equals the value of the function at x bar. The second, whether x is an isolated point of the domain, and here you don't have to add anything. You are already there. You are done. Okay? And now, another definition that I will use a lot, it is just a natural definition, but I have to state it. So let f be a subset of E, possibly coinciding with the whole E. A function f, defined on E with real values, is said to be continuous in the set F. So continuous not at a point but in a set, but very simply if it is continuous at every point of the subset capital F. Here the example. Here we have f of x is 1 over x. Of course, E is equal to R minus 0. And I already gave you today the graph, and the exercise is to prove that f is continuous at r minus 0. The proof is, it is very simple. I write here the main steps. First, one has to recall that continuity is defined as a notion for points in the domain only. So in this case, for x different from 0. Furthermore, all points in E, r minus 0, are accumulation points. So we just have to verify the limit. Moreover, for every x different from 0, x bar, but not only, we have that the limit for x going to x bar of x is equal to x bar. This is really stupid limit. And by algebra of limit, in particular, the ratio, okay, the limit of the ratio, by algebra of limits, we have at the end that the limit for x going to x bar of 1 over x is equal to 1 over x bar. And this is the end. So f is continuous. And what about 0? What about 0? It is a discontinuity point. But the funny thing but this fact does not affect the continuity of the whole function 1 over x. And this is really the end. So this is why I told you that discontinuity is not the contrary of continuity. F is a continuous function because it is continuous in all points of the domain, but at the same time has a discontinuity at 0. But don't tell me that f is not continuous. This is false. This is a mistake. Other examples of continuity, and then I think we are done, at least for these videos. So the example is 1. So we have powers. F of x is equal x to the m. M is a natural number. Domain of f is equal to R. We know that the limit for x going to x bar of x to the m is equal to x bar to the m. And so f is continuous on R. The second very similar conclusion is for the function sine. And so before consider the function sine, is we can say that by the algebra of limits, we can conclude that all polynomials are continuous on R. First. Second, f of x is equal to sine of x that converge to sine of x bar for x going to x bar, and this is continuous on R. Third, f of x is equal to cosine of x, and again here we studied that this converges to cosine of x bar for x going to x bar, continuous on R. Then the fourth example is about tangent. The tangent is sine over cosine, and E here is the domain, the natural domain is R minus P halves plus half twos on the circle. And this is continuous on all points of the domain, and remember the graph of the tangent. So you have this points p over 2 minus p over 2 and so on. The function is periodic with period equal to p, and this is the shape of the branches of the tangent, and in a completely analogous way we can define the cotangent and E is equal to R minus Kp with K in Z, and again we have continuity on the whole E. Then other transcendental functions, but that are very important. F of x is equal to E of x. This is the function of the growth of the pandemic now. And this is continuous on R, but I won't prove it. If you want to have the full construction of the exponential with continuity, and go to see books, and 7 f of x is equal to log of x, continuous on its domain, which is 0 plus infinity, and again here we can draw the picture. This is y equal to x. This is e to the x. And here it's sort of mirrored. This is log of x. one is the inverse of the other, and another nice function is, as usual, the sine of x equal to r, and this is continuous at r minus 0, so not in the whole domain, and we have a jump discontinuity at x bar equal to 0, and the size of the jump is equal to 2. And next thing I have to tell you concerns the algebra of continuous functions. It is very natural because it is inherited from the algebra of limits, and so as usual the hypotheses are E in R, X bar in E, F, G from E to R, and both functions are continuous at X bar. And then we consider, for instance, the sum. So the question is f plus g continuous at x bar? So there are two cases. First case, consider the case with x bar also an accumulation point. So we have E intersection DE. We have f of x goes to f of x bar. G of x goes to g of x bar when x goes to x bar, because when x bar is an accumulation point, continuity at x bar reduces to computing the limit. Then, by the algebra of limits, we have that f plus g of x converges to f plus g of x bar. And then f plus g is a continuous at x bar. Second case, is when x bar is an isolated point of E, not of x bar, of E. Then, since every function is continuous on the isolated points of its domain, we have that f plus g is continuous at the point x bar. So, in every case, f plus g is always continuous at x bar. Notice that what we said here, we relied on the algebra of limits, or here we relied just in the isolated property of continuity on isolated point of f. The conclusion here is extremely simple. The conclusion is that we can replace it by sum by dot and also by the ratio. But in order for the ratio to be well defined, f over g, one has to require the g of x bar is different from 0. Okay? And this is very natural. So the algebra is extremely natural. The last thing I want to say about prolongation by continuity final remark is the following. A function, I want to tell you again because perhaps I did not stress it enough. A function can be prolonged by continuity at a point x bar if and only if the limit for x going to x bar of f of x is equal to f of x bar is in D, sorry, not f of x bar, is equal to L, and L is real. Okay, and then we will define f tilde as we saw before. Okay, stop here with this part of continuity and continue on next video.